ജോയിൻ ചെയ്തോ?
കേൾക്കുന്നുണ്ടോ?
ഹലോ, കേൾക്കുന്നുണ്ടോ? ഇപ്പോഴും കേൾക്കുന്നുണ്ട്. കേൾക്കുന്നുണ്ട്. ഇപ്പൊ ഇപ്പോഴും കേൾക്കുന്നുണ്ട്. ഇതിനെന്ത് ചെയ്യും?
Hello, Dr. Sunny. Shall we start? I'm not able to hear anything. Am I audible?
Yes, sir, you are audible, and it is the slides are visible also.
Okay, so just inform me whenever to start. Yeah.
Yeah, we'll start soon, sir.
Shall we start?
Okay, now.
Shalini,
Sir, okay, okay.
let's start.
A very good afternoon to all the esteemed attendees here. I am Dr. Sunitha Vijayan, Junior Scientist from the Transportation Planning and Engineering Division at NATPAC. It gives me immense pleasure to welcome you all to the TransTech Talk series organized by KSCST, National Transportation Planning and Research Center. This talk series is yet another unique venture of NATPAC, which we provide a platform to experts in the field of transportation engineering to share their knowledge and expertise with us. These talks will give us insights into the latest developments, emerging trends, and cutting-edge technologies in their field. Today, we are hosting the 13th talk in the series, and we have with us a distinguished speaker, Professor Ashish Bhaskar, Professor of Civil and Environmental Engineering at the Queensland University of Technology, Brisbane, Australia. Professor Bhaskar will be sharing his valuable insights on the topic, real-time simulation of large urban networks, leveraging big transport data. To begin with, I would like to request Srimati Shalini PN, Senior Scientist, Transportation Planning and Engineering Division, NATPAC, to deliver the welcome address. Over to you.
Good afternoon, everyone. I'm delighted to welcome our chief guest of the day, Professor Dr. Ashish Bhaskar, who is the professor in School of Civil and Environmental Engineering, Queensland University of Technology, Brisbane, Australia, who has warmly accepted our invitation to deliver a technical talk on the topic real-time simulation of large urban network and leveraging the big transport data. Professor Ashish Bhaskar is an accomplished researcher in the field of transportation engineering. Moreover, he is a very approachable and down-to-earth person. And we are honored to have him here today to share his expertise and knowledge with the research and scientific community here. On behalf of NATPAC and all of us assembled here, let me welcome you, sir, to this event. I'm sure that this will be a valuable learning opportunity for all of us. And on behalf of NATPAC and all of us, let me welcome all of us to this event. I welcome all the students, researchers, academicians, and the transportation fraternity as a whole to this interactive session. Once again, welcoming you all to this event. Thank you.
Thank you, ma'am, for a delightful and eloquent welcome note. Now, I would like to invite Sri B. Anish Kini, Scientist, Transportation Planning and Engineering Division, NATPAC, to introduce our esteemed speaker to the audience. Please, sir.
Thank you. Good afternoon, all. It is my honor to introduce our esteemed speaker for today's TransTech talk, Professor Ashish Bhaskar, who is a renowned professor in School of Civil and Environmental Engineering, Queensland University of Technology, Brisbane, Australia. He is a chief investigator for QUT, Center for Data Science, where he also co-leads business and engineering systems research domain. His expertise includes transport, big data analytics, modeling, simulation, and control. The focus of his current research is on addressing the sustainable transport and mobility challenges, including road traffic congestion, safety, and their detrimental socioeconomic and environmental impacts. Together with his team of researchers and collaborators from government, industry, and academia, he is working towards evidence-based decision support, management, and control of multimodal transport system. He holds a PhD in Intelligent Transport Systems from the Swiss Federal Institute of Technology, Lausanne, Switzerland, Masters in Transport Engineering from the University of Tokyo, Japan, and a Bachelor's in Civil Engineering from the Indian Institute of Technology, Kanpur. He is a chair for the World Conference on Transport Research Society, SIGC3, on Intelligent Transport Systems, the editorial board member for the Journal of Big Data Analytics in Transport, and the International Journal of Intelligent Transport Systems Research, member of the Transport Research Board, Standing Committee on Transit Management and Performance, and adjunct faculty at the Indian Institute of Technology, Madras, India. Please join me in giving a warm welcome to Professor Ashish Bhaskar for delivering a talk and sharing his valuable insights. Welcome you, sir.
Thank you, Dr. Anish and Dr. Salini. It's a pleasure for me to deliver this talk. And those who have attended CTRG, this year, I mean, the slides which I'm going to present now are actually the one which I had presented at CTRG during my keynote speech. But I'm going to try to present in a slightly different manner. Now, to begin with, I would just like to introduce our university here, the Queensland University of Technology. And it's a big university in Australia. We have around 50,000 students, and 16% of them are actually international students. We have different faculty. Let me use my pointer. Yeah. So I belong to the Faculty of Engineering, but we have 5 different faculties here. And QT is ranked second in as one of the young universities in actually Australia. So in terms of the transport research at QT in the School of Civil and Environmental Engineering, we have around 6 academics, as you can see here: Professor Alex, Professor Shimul, Professor Jonathan Bunker, myself, Mark Miska, Dr. Mark Miska, and Dr. Shams. We also have different centers at QUT, the Center for Accident, Road Research and Safety, CARSQ. We have QUT Center for Data Science, where I am heavily engaged, Center for Robotics, and Center for Behavioral Economics, Society and Technology. So basically what I'm trying to say here is that in addition to the civil engineers, there are other researchers also that work heavily in the area of traffic and transport engineering. Now, QUT is situated in Brisbane, one of the beautiful cities in Australia. In fact, Brisbane is going to host Olympics and Paralympics in 2032. So if you plan to, take sabbatical or visit some university, I would say that's the best time to come to Brisbane. We have 2 campuses. The one which is the Gardens Point campus is located near to the Brisbane CBD area. Plus we have other campus which is around 5 kilometers from the Gardens Point campus. And our engineering faculty is located at the Gardens Point campus. Well, what you see in this image is there is a motorway section connecting Brisbane North with Brisbane South. QUT is located along this beautiful Brisbane River. We have this bicycle and pedestrian only bridge, which is connecting again the north and south part of the river. We have a bridge where only public transport is allowed. Plus, on the river, you can see that we have ferries. Now, this photo not only introduces QUT, but also the multimodal aspect of our transport infrastructure. So transport system is actually a multimodal transport system. We have different modes of transport. They may be managed by different agencies. For instance, the motorways are generally managed by the state authorities, whereas your RTL network is managed by the local agencies. And similarly, public transport may be managed by the state or by the local agencies. Like in Brisbane itself, we have Department of Transport and Mains Road managing motorways, Brisbane City Council managing the RTL network, and TransTech, which is a division within the Department of Transport and Mains Road, is managing the public transport network. Now, they are different agencies managing one complex multimodal transport network, but as a road user, we only see it as one complex multimodal transport network. So all the agencies have to talk to each other and actually try to solve this complex problem of transport systems. Thankfully, the road infrastructure is covered with a number of sensors. I'm just taking example of a few of the sensors here. And these data from these sensors are available either, there is an automatic collection of data set available in the center, or maybe, in some places we are doing the manual counting. Anyways, the data from these road infrastructure or our transport system provides opportunities to go for evidence-based decision support. And that leads to, all the way from smart congestion management to strategic planning of infrastructure. So what you see here is actually a transport system cycle, but this system cycle is actually equally applicable to any other systems. So we have the mesh of sensors over the network. We use that data set from the sensors to make some intelligent decisions to manage our congestion and strategic planning for the future. Now, so my talk today is actually focusing on 2 aspects. The first aspect is transport big data. So I thought I would like to introduce some of the big data sites of our transport network. and talk about some of the opportunities and challenges which are there. And the second part of my talk is focusing on conceptual framework of the real-time traffic simulation, which is basically the title of my talk. Actually, this is a project that we have recently delivered to the Queensland Department of Transport and Mains Road, where we have implemented or we've done all the R&D for the real-time simulation of the entire city of Logan. So let me first start with the transport big data sets, because the knowledge of this might help you to have understanding of how we can utilize the data available from our large network to better manage to actually better perform simulation for the large cities. Before I start, I must acknowledge the various agencies that have shared their data with me over the last 10-12 years since I am at KUT in Australia. Without their data set, whatever research I perform is almost impossible. Plus, I will also acknowledge all the collaborators, both within KUT and actually overseas. And few of them you can see also are actually in India. So a lot of my, I would say, research is actually supported and actually influenced by the discussions I have with my colleagues. Last but not the least, my research team. I mean, they are the one who do all the hard work, and basically I just present their work as my work. So then, like I have a pretty good research team of my current and the past students who have worked with me on various projects. And what I will be presenting is actually some aspects of that. Let's start with the Bluetooth Max scanner first. One of the data sets which I actually, when I joined KUT in 2011, at that time Bluetooth Max scanners were one of the hot data sets available. In fact, not much knowledge was there regarding how this data set is actually collected and how we can use it. And one of my initial research was to have understanding of this Bluetooth Max scanner data set. Well, the way it works is that you have a scanner. This scanner will try to scan the MAC IDs of the active Bluetooth devices within a scan zone. This can be 100 meters, 150 meters, or 250 meters, depending on where you are installing the scanners. If you're installing the scanners on the arterials, you will aim for 100 to 150 meters. I mean, the concept is you want to have the vehicle at least for 5 seconds within the scan zone. So on the arterials, the speed is quite low. That's why your scan radius is 100 meters. But if you put it on the motorways, you might like to have it for 200 meter scan zone. Now, each time you have a Bluetooth equipped MAC ID in the discoverable mode, this scanner just tries to capture the MAC IDs of those electronic devices. And because these MAC IDs are unique and the corresponding timestamp, it basically captures whatever device is observed within the scan zone. Now, imagine the network with a mesh of such scanners. For example, what you see here, this is the entire Brisbane region, and we have more than 2,000 scanners over the entire Brisbane city. Each and every signalized intersection has a scanner associated with it. And that's the Southeast Queensland, that's the state of Queensland. We have more than 1,000 scanners by the Department of Transport and Mains Road over the whole network. Now, if you have these sensors or scanners over the entire network, then if all these scanners are time synchronized, then what you can do is you can trace the movement of the MAC ID over the entire network. And that's what this Bluetooth Max scanner is actually doing. So imagine I have a scanner at 2 locations, and I can basically use it to actually capture the MAC IDs. If I map the MAC IDs, I know the travel time between those 2 locations. Let's have a look how big this data is. I mean, this was just a random selection of your data set for 1 month from the motorways and from the RTL network. So around 450 scanners on the motorways, around 950 scanners on the RTL network. What you get is around 8 million records per day in the city of Brisbane, which is approximately equal to 8 GB data per month is what actually you extract from these scanners. The good thing is this data set is very well structured. You have an encrypted device ID, you have area ID, where the scanners are installed. You know the time when that MAC ID was observed and duration for how long it was observed at that specific location. There's a very well structured data set which basically you can get from this mesh of scanners. This is just a snapshot of the travel time profile between 2 locations. So if I match my MAC ID at location A and my MAC ID at location B, and if I just get my travel time, I've just plotted that here. Here, x-axis is the time, y-axis is the travel time in seconds, Each of these subplots represents one specific day from midnight to midnight. The first column is Monday, second is Tuesday, and so on. And you can see that it's quite noisy. I mean, when you match the MAC IDs, we do not know what those vehicles are or what those devices are being transported by. So we are just matching the two, and we only know that, okay, the device was at location A at time T1, location B at time T2. We do not know what happened between A and B. That's why you have all this noise that you see here. You can apply some statistical filters. That's the initial work we did long time ago. We applied MAT3 filter, and basically you can remove some of the noise, or most of the noise, I would say, and you can get some travel time profiles for that link or the section for which you're interested in. And you can see that, look, your Mondays, Tuesdays, Wednesdays, this was a public holiday, so that travel time is very different from the other Wednesdays. Saturday and Sundays, you hardly have congestion on that section. Fridays, again, is very different from your other working days. So it gives you a very rich information, and the agencies are very happy in the beginning with this data set, because earlier they used to do floating car survey to get that travel time profiles, which is an ongoing cost to the department. So in this case, now you have a seamless estimation of travel time for the entire city. We are thankful to both TMR, or the Department of Transport and Mains Road, and the Business Study Council for sharing their data set with us. This data comes in a form of simple CSV files, as you can see here, but this is a huge data set. Imagine I have a sensors installed over the entire city, 3,000 sensors, getting 24/7 data set. This becomes a huge data file. So one thing which I did like a couple of years back was I engaged some of the students from computer science and asked them, can they help me to do some visualization of this data, because these CSV files I'm getting every day, they are huge. Every month I'm getting 8 GB of data, 8 million records per day. I don't know what's behind it. So we started working on some visualization aspect there. So you get the data set, you do the analytics. That was mostly the research component. In fact, I had like 2 or 3 PhDs who have worked on this data set, but then the visualization was something that really explored further. And that's why I want to highlight that, especially the visualization techniques or visualization expertise are really helpful for a lot of the work that actually you will be doing down the line as an intelligent transport engineer. So that's a dashboard that we built for the entire city of Brisbane. You click on a link, so you do all the analytics, put that into your database, and you can get the speed profiles, your travel time statistics, which are there for that link, and so on. Now, we built this dashboard in-house first, and it was liked so much by the department that we basically also implemented the same dashboard in the Department of Transport and Mains Road. Then, now, if I have my travel time characteristics for my entire city, and I have a historical profile for my last couple of, let's say, months and days or actually years, I can use it to actually do some predictive analytics and basically do some forecasting. One of my PhD students, she worked on this traffic forecasting and basically tried a couple of machine learning algorithms. And in fact, I still have one more PhD student who is from computer science background, is actually working on a lot of, I would say, modeling on actually forecasting the traffic conditions. So I won't go into those models, but what I like to highlight here is that never use machine learning blindly. I mean, this is one of the buzzwords that we all are using these days. I see a number of papers where people talk about applying machine learning on any kind of problem, on any kind of data set. And I've also seen a couple of cases where I don't think machine learning is needed, but they have just applied it. So what you have to keep in mind is that don't use it blindly. Understand the fundamentals. You should have a strong understanding of the foundation behind the machine learning approach or the modeling that you're doing. Look at the problem, look at the data set. Machine learning is a very valuable tool. It's a very powerful tool that can help you to solve a number of problems, no doubt, but the critical thinking cannot be replaced there. You should be always questioning your data set. You should always be questioning your methodology. You should always be asking, why am I doing whatever I'm doing? So that critical thinking component should not be ignored. Like one of the students who I have worked with in the past, he was from the computer science background. He applied a number of algorithms to do the forecasting, and he said, look, this algorithm is giving me better results than the other one. But for me, that is not what I'm aiming for. What I aim for is an algorithm that basically can help me to understand the overall process. So if I have two algorithms, one of them, let's say, giving me an accuracy of 95%, other one giving me an accuracy of 90%, I don't care between 95 and 90% based on my application. What I do care about is if I can explain better with my 90% of accuracy, I mean, if I can able to understand the algorithm better, the one which I'm able to understand better is the one I'm going to focus on. So transparency and explainability is an important aspect that should not be ignored in your entire modeling. Interpret your results with caution and be aware of the biasness. Again, the way you have trained your data set, on what aspect you have trained, can I generalize my results? I think those are the things that you should always be asking, and not just be focusing on your end output or your end accuracy directly you might get from the algorithms. So never use machine learning blindly. Now, I want to highlight a few other things that helped us in the data visualization. On the same dashboard which I showed earlier, I asked the student to show me the missing data points, or show me how much size I'm obtaining for a specific link based on my travel time profiles. So here for this specific link on the Brisbane network, and for the month of July, I think it's 2019, from midnight to midnight for the entire month. What you see here is different color snapshots. So every 1 minute or maybe every 5 minutes. I don't remember what the time period was, but I think it's every 1 minute. How much samples you are observing. So red color represents there is no sample, or sample is between 1 to 2 or no, and green represents they are really good samples. So what you can see from here is between 6 a.m. to 6 p.m. Generally, that's the time period when I'm getting most of my samples. During the midnights or the late night, yeah. Is there any question? Okay.
So no questions. Probably
Okay.
somebody unmuted.
Okay, no worries. So what I'm highlighting here is that obviously this specific link has a very good sample size, not a problem. If I go to some other link, that's just a nearby link, you can see that for the same month, you have a lot of red lines. So sample size is varying from one link to another link. Maybe if I go to some other road, here the sample is not that good, whereas one of the roads in the far north has excellent sample that I need. But some of the days, maybe the scanner was not working. And then that's the other direction of the same road. So what I want to highlight here is that your sample size is going to vary over both space and time. And when I'm talking about the travel time estimates from the Bluetooth, it is basically an average estimate for the various samples that I have observed. So you have to take into account basically the confidence that you might have in your estimation. So never ignore the confidence. Always have a look on the fundamentals or the basics from where the data is collected and how much confidence you have in your estimates. A lot of data these days is available open source also. I mean, the Bluetooth is not open source, but our loop-directed data set for the entire city of Brisbane is freely available. You can download it directly from the BCC website. We have around 1,000, I would say, traffic controllers for which they have given the data set, which has around 7,500 loops-directed data set. If you start downloading it, it might be around 5 GB or sorry, 0.5 GB a day is what you will be downloading from the entire city of Brisbane. Now, loop, as we all know, is going to give you the volume values very accurately. So loop is the one which is going to give you volume, definitely. I will not trust the speed estimates of the loop on the arterials, but I will definitely trust the volume from the loops. Bluetooth is giving you travel time. So that actually opens opportunity for you to fuse these two data sets together because they are complementing each other out. And that's one of the work which we did long time ago. How do we perform data fusion of Bluetooth and loops? So if you perform that fusion, I mean, if you try to integrate the two together, then you will be able to get far more traffic statistics. You will be able to get the travel time seamlessly, or you can even estimate that density. So we have worked on actually some of the models by which you can fuse the loops and Bluetooth to get the density also on our arterial sections. So what I want to highlight here is that data fusion is also one of the important aspects that should be taken into account, that you try to work on the strengths of one data set against the weakness of actually other. And there are a number of mathematical models that actually you can apply for actually fusion. So that was on the Bluetooth-based travel time statistics or density estimates, and the department were very happy with that they're able to get a lot of information from Bluetooth. But actually, as a part of our research interest, we wanted to get more from the Bluetooth. And one thing that you can also get from Bluetooth are the trajectories of your Bluetooth devices. For instance, if I so these are all these dots that you see here. These white dots are the intersections on which I have the scanners. And this is actually one of the MAC IDs which I have traced around early in the morning. And the same MAC ID in the evening is the one that you see at the bottom. So all the arcs that you see here are basically the hopping from one intersection to another intersection, as observed by the scanners. And you can see there is a portion of the network where you are missing that device. It can be because of various reasons. Your scanner has a scan capacity. It may or may not observe a device, even though the device is traveling through it. It may not capture it because it has a scan capacity. Business City Console scanners have a scan capacity of, I think, 14 MAC IDs per scan cycle, and the scan cycle, I think, is 14 seconds. So the maximum they can scan is, 5 seconds. So maximum they can scan is 14 MAC IDs every 5 seconds, something like that. But anyway, there is a capacity that they can scan. So you are not scanning all the devices, or there can be other reasons why they are not scanned. As you can see, this MAC ID might have traveled over these 3 scanners, but actually I have only scanned it here and there. Anyway, so it can give you trajectories. And in fact, like a couple of years back, one of my PhD students actually worked on an algorithm to actually identify how you can retrieve the Bluetooth trajectories, given that your observations might be only from some locations. For instance, imagine my Bluetooth observations are from these blue circles only. Then a vehicle might have different possibilities to go from point A to point B. So that leads to a very interesting problem, how you can have some confidence or come up with some models that can retrieve the vehicle trajectories with the observations only at few locations. So that was one of the work we did long time ago. I think this guy did PhD in 2015 or 2016 with me and finished around 2017. But we can actually come up with those models. Recently, another student worked with me on a very interesting problem. Basically, on the Brisbane CBD area, as I said earlier, the scanners are basically scanning over a scan zone of, let's say, 100 meters. And, or in fact, in the case of BCC network, it's around 150 meters. So each of these circles that you see are actually 150 meter radius circles. So, and center point is the dead dot for, I feel, the scanner is installed. Now, because the scanners are going to overlap a lot. And if I look at my figure on the right or the animation on the right, this vehicle is moving along one of the roads here. But each time you see a blinking scanner, it might be scanned by scanners at different location. So for this specific vehicle, although it has moved along this Eagle Street and then this Creek Street, only this portion, but this guy might have been observed at Adelaide Street, scanner number 3 also. Might have been observed also at scanner number 7 and 8. So how do you actually get a most probable trajectory of the vehicle, given that if I install my scanners at a very dense network, I might have a lot of noise. I might have a lot of errors in my observations. So that's another piece of problem that actually one of my PhD students has solved recently by actually looking at some of the algorithms that can help us to actually get rid of this noise in the movement of the vehicles. So what I want to highlight here is always go to the fundamentals of your data collection, and that might help you to have better understanding of what noise or what errors it can induce, and then addressing those noise and errors is actually a contribution to the scientific world. Let's now talk about a third-party vehicle telematics data set. Like this is another interesting data which is now widely available. It is the position or GPS position of the vehicles as they move over the network. We are doing a project with the Department of Infrastructure where we are trying to study the freight logistic data set. Basically, the freight companies are sharing their GPS positions. So we are actually working on that. And as part of that project, we have basically, like highlighted one data life cycle component of it. We have said that, look, these days there are different service providers which are basically providing services to various vehicles or the freight movements. These service providers are collecting detailed vehicle telematics data, and then you have different aggregators. These aggregators are buying those vehicle telematics information, which is nothing but the vehicle telematics information is the position of the vehicles at different time step, plus other detailed information like whether the engine was on or not, what was the G-force value, and actually all those things. Very detailed information from the vehicles. These aggregators are buying this from various service providers, and then they are selling it to various agencies. For instance, in Queensland, we have like maybe the service providers might be some of the telematics companies or TomTom or actually other agencies which are giving services to the various vehicle operators or owners. Whereas aggregator is, let's say, Compass IoT, which is buying those data set from these service providers, aggregating it and selling it off further. Now, I want to highlight this, like for example, this is actually my own personal example. When I was going to India in December, and we basically a family of 4, myself and my wife and my 2 kids. All of us have actually phones with us, and we are using Life 360 as one of the apps to track the movement of each other where we are. So Life 360 is actually one of the location-based service providers. It helps you to actually track the movement of your family members. Now, we were in a taxi going to the airport, and that's a screenshot I took from my phone regarding how it is treating us as 4 different people. And basically, you can see that Life 360 at this stage is showing us that we are on 4 separate cars. So that service provider is taking this information and then sending it back to the aggregators. I'm quite sure that Life 360 should be smart enough to accommodate all 4 of us as one group of travelers, because we are from the same family, and perhaps put them in and assume that there's only one vehicle. But it can happen that I might be in a separate car than compared to my wife. So these things, these things leads to some inherent noise in the way the data is being collected. So if it treats as 4 cars on the road, then basically it is giving us 4 sample size. Or if it treats as 1 car, it is only going to give us 1 sample size. But actually, all of us were in the same car in 1 car only. But from this video shows that it might have treated us as 4 cars. Anyways, what I want to highlight here is that there is some inherent noise and biasness in the data set, which may not be, which is something that you might not be able to address, but you should be acknowledging that okay, these kind of noise in the data set can lead to some errors in your analysis. So acknowledge the biasness which can be there. Some of them you can address by applying some of your own, I would say, knowledge of the system or the way the data is collected, but some of them you might not be able to address, and that might lead to further errors in your end findings. Now, the data set we got from Compass IoT, one of the service providers, one of the aggregators in Queensland. I would just like to show that. This is for the entire city of Logan, and it is a very rich vehicle trajectories that you can get from that data set. For the whole city, and each of these that you see here, like the different color, different type of vehicles. So these aggregators can really give us a good amount of data set that can be utilized for various research and development purposes. And that for the city of Logan, what we did was, if I look at the trajectories along an arterial network, so I'm using the same data to just present how we can look at the data set. Let's say this is one of the motorway, one of the arterial corridors. So we have intersection number 1 between Compton Road and the Kingston Road, intersection number 2 between Logan Road and the Compton Road. So I will just stretch it along the y-axis. So that's y-axis is my space. So my first intersection, my second intersection. X-axis is the time. And these are the trajectories that we have just plotted. I mean, that data set that we are getting here is, I think, every 5 seconds or 10 seconds. So that's each of the dots here are the positions when we have got when we have got the data, and then we have just done a linear interpolation. If we superimpose the signal timings also, then what we can see here is basically that linear interpolation is not the right interpolation. You might, like for example, this vehicle cannot cross the intersection during the single dead time, and that's where different models are developed by actually integrating the shockwave theory with the signal timings to have more accurate profiles of those trajectories. And a lot of research is being done in this space where people have used this tracking data set to estimate the Q lengths and actually other parameters of the traffic signal operations. So in fact, these data sets provides a lot of opportunities for us, like you can use it to have proper performance measures of your entire arterial network or your entire network. What I've shown here is one of the projects that we are about to start with the department, where we want to utilize all the available traffic data sets, whether it's a trajectory, loops, or Bluetooth, whatever is available. We want to use it to come up and with an automated way of defining the performances of your transport network. In fact, the focus here in that project is primarily on the arterial network. Come up with a new set of indicators that actually these data sets can provide, and then utilize it to do some smart arterial network optimization. So better planning of your traffic signal timings. And then whatever you do here is going to impact the way you're going to control your transport system. So that's for the road, I would say mostly the vehicle data set. I might now like to discuss about the transit data. And so for the transit data, I will have to talk about the GTFS data set, the General Transit Field Specification. This data is now widely available. I know even in India, IIIT has been managing the Delhi GTFS data sets, and basically various transit agencies have made their data publicly available. In fact, a couple of years back, when I was trying to play with this data set, I do not have any knowledge about how I will be able to download the data from the open data portal which TransTech has shared. It's a real-time feed that you can download directly from the server, and various agencies have done it now. So I hired a computer science student to again work with me to help me to smoothen the process of how you can download the data from your transit server, bring it to a proper database management system, and do some visualization. So once we have done it, we basically made the code open source. Anybody now, basically it's available on at least GitHub. You can use those codes to download the data from any server. And in fact, I will be happy to actually also share the details if you need. I think with that open source framework, you can download the public transport data set for maybe even the entire city of Delhi. The data is quite huge for our Brisbane network. We have around 25 GB of data per day. Why it is so huge? Because we have around 1,400 buses, we have around 20 ferries, around 100 trains, around 14 trams running over the entire southeast Queensland. And every 2 to 10 seconds, you are getting the real-time position of those vehicles. And you also have, like these are simple text files that you get, and they're very structured files. But if you are extracting them every 2 seconds, it basically is a huge amount of data. And once we get the data set, the student has further visualized it on a Tableau. That was an offline visualization we had done at that time. Recently, I have hired a few more students, and they are now working on real-time visualization. So what you see here is the dashboard, where in the previous case, we were downloading it from a TransTech server or any transit server. In this case, we have processed the data and visualizing it on the map. So it's a real-time visualization where each of the circles represents a specific type of public transport vehicle. The arrow shows the direction in which it is moving. The color represents if it is on time or is it delayed. So red color means it is delayed by more than 5 minutes. and the green means that it is running on time. Now, all these informations are in the general transit feed specification data set. We are in the process of cleaning this code, and ultimately, like in next few months, I'm also going to upload the code for this real-time visualization also on the same GitHub. So what I want to highlight here is that these data sets are openly available. It requires some efforts to come to a point where you can bring it at one specific location, but then once you have it, then you can perform a number of activities on it. For instance, we have looked at defining the congestion profiles of the public transport network. So these are your congestion maps for the high frequency buses on the Brisbane network for different time of the day. And once you have these congestion profiles, I mean, you can basically look at identifying where the hotspots are, identifying how, if you can do some changes in your timetabling or in your scheduling, what impact is going to bring in. You can use it to identify how much energy is being consumed by my public transport network. And if tomorrow, if we have electric buses, well, how much benefit we can have in terms of your greenhouse emissions and other environmental factors. So once you have the data sets, a lot of analysis can be done. We also looked at some of the incident data set, like this is incident management system data, which is available in Queensland. We looked at integrating the incident with the GTFS to understand, okay, if I have accident on the road, and this is the actual accident, which are the buses which are impacted and for how long they are impacted. Those kind of integration might help you to have better understanding of, the impact of incident on the transport performance. Last but not the least, I will talk about another data set, which is automatic fare collection. Each time you have when you board a public transport vehicle in Queensland, or when you alight, you have to use a smart card. So in our case, we exactly know when a passenger is boarding and a passenger is alighting. What you see here is an arc. Each arc represents one passenger at the time when it boards and the time when it's alight. That's your Brisbane. This is Gold Coast. That's your Maroochydore, the Sunshine Coast area. And this visualization just shows one complete day snapshot of how people are moving over the entire Brisbane and the nearby satellite cities. We have used it to actually understand various type of passengers on the road network and proper, I would say, passenger segmentation, and use it also to actually better understand the transport coordination. This can also be utilized to actually study the patterns that you have on your public transport network, and those patterns can help you to better manage or better plan for your public transport. Yeah, so what I want to these were some of the examples which I've shown, but I wanted to just highlight a few key messages from the traffic data. One is data is a very valuable asset and it should be treated as an asset. But if you cannot extract the value out of your data set, then no matter how big the data is, it's actually useless for us. So it's a valuable asset and it can provide some new insights that can help you to have some more informed decision making, but you should learn how to extract the value out of it. Never use it blindly. Please never ever trust your data. Always have questions that how much accuracy you have in it. Understand the source, how the data is being given to you. Real data will be very, very messy. You have to basically look at ways by which you can reduce the errors or the noise in the data set, and always look at how much confidence you have in it. Data fusion is actually one of the areas that you should definitely focus on. Different data sets can give you, can complement each other, or even if they are giving the similar information or the information for the same type of parameter, you have to look at how you can basically fuse the two together so that you only have one single point of truth. And again, machine learning and AI, these are the buzzwords widely used, have a lot of potential. They are really great tools, but please never use it blindly. So that's the message I have for the traffic data side of it. If you have questions, you can ask before I move to the next part. Otherwise, I can just start. I can just move to the next section. Do you have any questions so far?
Hello.
Yeah.
Sir, I want to know how the number of sensors are fixed. Like if the number of sensors are more, then the amount of data will also be greater. So, is there any method to optimize the number of sensors?
Number of sensors. Which sensor we are talking about? Is the Bluetooth or like any sensor?
Bluetooth.
I mean, so your question is, the more the number of sensors, the more data set we have, right? So is there a way by which we can optimize the number of sensors? Means we want to minimize the number of sensors on our road network, so that by putting in less number of sensors, which is going to cost us less, but we should be able to get as much information as possible. Is that what you're asking?
Yes, sir. Exactly.
Yeah. I mean, in fact, that was a very interesting research. I think should be a problem for Indian condition. Definitely. When I started in 2011, when Brisbane City Council was installing the Bluetooth track scanners, I actually went to them and said, look, we can look at the ways by which we can optimize the locations where you should be putting the scanners in, because by doing so, you can reduce the cost of installing the scanners, and you don't have to install the scanners at every place. And they said to us that, look, because the scanners were not that expensive, scanners were only $500 each. And what they did for actually Brisbane City is they installed the scanners at each of the intersections where you already have existing system in terms of traffic signal control. So every traffic signal controller, the scanner is just basically here. You can see this is traffic signal control box and a scanner, and it is using the same infrastructure that is used to control the traffic signals. So you have a fiber optics wire going in that signal box or the signal controller, and you are using the same internet or the internet to actually extract the data set. So for them, the cost was only, let's say, maybe $1,000 for each intersection. So they said you're going to install it on all the intersections. Now, that's for actually Brisbane. Now, if you have to install the scanners in, let's say, some of the conditions where you have less budget, then obviously you have to look at what do you want to do with these scanners. Do you want to extract the travel time, or you want to extract the origin destination matrices? What is your end application? And based on this, you will say, look, for this end application, I will identify what are my critical node points on my network, and then try to install the scanners on those critical node points so that I should be able to make a better estimate that I want to estimate at the end. So if your objective is to get the travel time along the entire corridor, I will just put these two scanners at the entry and exit of the corridor. If your objective is to get the OD matrices, then I would like to put the scanners at the critical intersections on which you are interested in the OD matrices. I hope that answers your question.
Yes, thank you, sir.
Sir, would like to know the OD matrices generated, whether it be vehicle type, vehicle category wise, or trip purpose wise. Is there any possibility of getting the OD matrices categories like this? And also the another query is how the interface at the end user is being practiced in Brisbane after collecting all the data, that after the data acquisition process, how the decision support is being given to the end user. What is the interface that is being practiced there for a real-time transport management? Okay,
so the first question is if I'm going to get any OD matrices from Bluetooth, right? Or any, is it based on, do we know the trip purpose or not? Again, I'm not talking about the OD matrices in my presentation yet, but yeah, if you're talking about OD matrices from Bluetooth, see, Bluetooth is a very small sample that you're going to get. Bluetooth, maybe you might be able to capture only 2% of your OD matrices over the network. You will not know what was the trip purpose. What you will only know is that a specific device has originated from this zone and has ended somewhere else. That's the only thing you will know. But what was the trip purpose, you will not know, because there is no other information attached to it. So trip purpose based ODs are almost impossible to get from these trajectories because you only know the trajectory of the vehicle. You have no other information, who is driving that vehicle, and what was the end application. I mean, what was the end actually purpose of that journey. So yes, you cannot get that, and that's where your household travel survey data set plays a very important role because it does capture those other details of your trip purpose. Your second question was how do agencies use these data sets or the analytics? So generally, like in the case of the travel time, the one I showed you earlier, for example, here. So these ones, or even if I go to that one, that's the kind of dashboards. Agencies basically have those kind of dashboards. In fact, this is the dashboard which we developed and implemented in the Department of Transport and Mains Road. So they have these kind of dashboards also, and these dashboards help them to actually, understand the performances of various indicators, of various sections. Then they also have other dashboards that basically tries to generate the performances, but they are more interested in the performance reports. So based on their let's say the network performance indicators, the analytics is done and the performance reports are generated. Now again, it depends on who that user is. So if I have to generate the information for the manager, for the higher management of the agency, then they are only interested in the end performance report. They want to know what portion of my roads are having, let's say, better speeds than the previous, or actually are improved. So they are only interested in those actually high level values. For them, the performance reports are generated. On the other hand, the actual traffic engineers working in the agency, for them, what is important is they want to see which of my sections are really congested and what time of the day they are congested. So these kind of like dashboards help them to identify, okay, these are my intersections, they are critical intersections. In fact, I've not shown in any of the slide here, but this dashboard can also help you to identify, rank your top 10 intersections which are really congested. So they get that information and then they try to see what's happening. Are the signal parameters really optimal, or do we have to fine tune them? So these kind of visualizations help them to identify the choke points in the network or the hot points, and then they try to look at interventions by which they can actually make the system better.
Thank you, sir. One more query in the chat box. Dr. Mahalakshmi Naidu has posted a question. In India, anyone using scanners, any such sort of data acquisition happening in India?
Yes, there is. I mean, in fact, I have worked with the SVNIT in Surat, Professor Srinivas. We try to play with the Bluetooth max scanners and Wi-Fi max scanners. I know IIT Delhi has done a lot of work, Professor Rita. She has worked on playing with the Bluetooth and Wi-Fi a lot. Interestingly, in 2013-14, so I actually purchased some scanners in 2011 as a part of my initial research grant, which are Bluetooth and Wi-Fi scanners. So we brought those scanners in India, and SVNIT did some experiments to collect the data, and we found that in India the Wi-Fi samples are far higher than what you're getting from the Bluetooth. But that was in 2014-2015 study. And then basically, a number of researchers started playing with the Wi-Fi scanners. So I know IIT Madras, SVNIT. I was having a chat with Dr. Ankit from IIT Jammu, and also one of my students, Dr. Anshuman, who is now in IIT Varanasi or IIT BHU. They're also thinking of installing the scanners and actually getting some data set for the Bluetooth and Wi-Fi. Yes, the interest has gained. The most of these Wi-Fi scanners or Bluetooth scanners are basically, they're not permanently deployed. They are just they can take it at the site and just collect the data, because the agencies have not fully integrated them. I think, as I said earlier, Bluetooth and Wi-Fi, we got a lot of samples for Bluetooth, but I believe now if you do the experiment, you might have much better Bluetooth sample also compared to Wi-Fi. The reason being is when we did the experiment in 2011 to around 2013-14, at that time, I think because a lot of the data that we get from Bluetooth, that is actually from the inbuilt Bluetooth of the cars. So they are dummy Bluetooth. Maybe 10 years back, Indian cars were not that much equipped with Bluetooth, but now I think Bluetooth is one of the basic necessities in that car. So all the new cars have Bluetooth basically inbuilt in them. You don't have to buy an off-the-shelf Bluetooth. So I believe now if you start collecting the data set, you might have maybe, at least in the metropolitan areas, you might have a better Bluetooth sample. But again, these scanners, some of the researchers have used, and but yeah, they're not widely used at this stage. But they are, I think, one of the potential sources of data set that can be easily utilized because they're not very expensive scanners. The cost, how much it cost? Again, as I said, like the cost of each scanner is not very huge. I mean, basically, it was at that time they said around $500 per scanner. So the cost of scanner is very cheap. I mean, 500 was like in 2014 when I checked. You can even build the scanner in house. The actual cost is you put the scanner in. The scanner is scanning the data set. How do you bring the data to your server? So like, if you want to bring it in the real time, then that might be an actually ongoing cost. Or you can just put your I would say download it offline once. But yeah, for real time, it is the other infrastructure which is going to cost a lot. But yeah, scanners are relatively much cheaper than directly video cameras or other equipments. Even I think SFNIT and IIT Madras have tried to build their own Wi-Fi and Bluetooth scanners, which they have used to collect around data set. But as I said, these are just temporary scanners that actually they have placed.
Okay, thank you, sir. Probably you can pass on to the next part of your talk.
Okay. So how much time do I have more?
Sir, it's okay that you take your time for completing it.
No worries. Yeah, perfect. So I will not talk about this case study that we have done recently for the city of Logan. It was a project funded by IMO Australia, and we tried to do all the R&D for real-time simulation of large urban networks. So AIMSL Live is one of the tools that, in fact, AIMSL was also part of this project. So we did R&D for them. I will basically talk about that part. Now, sorry? Yeah. So we are here simulating large urban networks. So I'm going to conceptually explain what we have done and actually how we have done it. I think one of you is not muted yet. I can hear. Okay.
Mute yourself.
Okay. Thank you. So we have let's say an urban network. So in order to perform any real-time simulation, what you need is basically an actually urban network first, on which you're interested in. That network, basically you can get your road profiles by, let's say, OpenStreetMap. You have to build a model out of it first. It's a graph model that you build. For example, for the city of Logan. So Logan is basically a satellite city to Brisbane. Is one of the suburbs, or I would say extended suburb of actually Brisbane area. We actually build a model for that, but this model is useless until unless we perform some calibration on it. So we have to calibrate both demand and supply for any transport model. In this project, we focus mostly on the demand side calibration, and that's basically called as the OD matrices. It's a dynamic OD matrix for the entire, let's say, day for this network. If I look at this network has 177 centroids for this one. So it means that the size of this matrix, each of this matrix is 177 by 177. And if you want this matrix every 15 minutes, then basically you can think of, like you have around more than 90 matrices for the entire day, and each one of them has 177 by 177 unknowns to solve. A lot of them are sparse, a lot of them are zero, but still, these are the unknowns that have to be estimated, and we do not know what those values are. Now, as I have discussed earlier, the transport network is equipped with multiple sensors, and these sensors basically, can give you a lot of information about what's happening on the road network, and that's basically a kind of a data lake that agencies might have, and this data might be available to you offline and actually also real time, depending on how much access you have on that data lake. Let's have a look on the and I want to also highlight that, as I said earlier, the data is never perfect. Real data is never perfect. And for this specific site, for this specific network, what we had was, we had loop detectors on the motorway. In fact, this is a very interesting network. We have a Pacific motorway, one of the expressways here. Then you have another expressway, which is Logan motorway. And that's the third expressway, which is the Gateway motorway. So this city is bounded by 3 expressways. One of them is state controlled. The other 2 are actually private expressways. So they are the toll roads. So we didn't manage to get data for the toll roads, but we were able to get the data for the state controlled motorway on the Pacific motorway, plus on the major intersections only. We had the loop directed data set available to us. So I know the counts at these red locations. We had hair-based speed data set, and I'm just presenting some of the links on which I have more confidence in my speed. So what you see is, for this entire city, there are certain sections where I have more I have one form of data. There are other sections, they have other form of data. So I have different views of the city by different data sources. Now, I have this data available to me for, let's say, for last 1 year for my offline data set. So you have the time series of these data sets available to you with for the whole 1 year. What you're interested in to identify the patterns in your historical time series data set. And what you want to say, let's say I have maybe 8 or 9 patterns in my history, and I want to build my models for each of these patterns. Now here, there are 2 research needs. The first one is, as I said, you have a lot of missing information. So a multi-sensor interpolation is one of the research needs that you have to do before you go for pattern mining, or even like you might like to utilize the pattern mining to actually do the interpolation. So data interpolation is one need, and data pattern mining is actually another need. These are the 2 research needs that has to be addressed, and that's what we have addressed as part of the project before going into any kind of simulation. Now, suppose you're able to get your patterns for that network. So I have offline data, I have filled the gaps, I've identified the patterns. What you have is you will take each of the patterns and come up with a representative traffic pattern for that specific I would say type of pattern. So you have a typical representation for each of the patterns. Now, I have a pattern-based profile with me. OD is what I'm interested in. What you do is, so you do not know the OD values. What you know is just the states. So you perform reverse engineering on your observations to come up with the best estimate of your OD matrices. And that's where the actual research is. How do I reverse engineer my observations to come up with my OD matrices? For this, let's say you have some algorithm and you are able to perform the reverse engineering. And then what you will have is, for each traffic pattern, you have the corresponding OD matrices. So you have your traffic states, or your, I would say, performance of the network, and you have the demand. And you end up into a repository of traffic states and the OD matrices. So this is what you do offline. And that analysis has to be done beforehand, before we go for a real-time simulation or the digital twin of the entire city. In the real time, I have the same model, and I might be getting my data in the real time. So I have my data, let's say, until the current time, maybe it's until 4 p.m. as of now. I will use my real-time data to identify that that my current day matches with which of my patterns in my historical repository. I identify that actually traffic pattern, and then from there take an OD matrix, the best estimate for that specific pattern. And then, because each of the days are different, I might forecast my traffic conditions for next 1 hour using some recurrent traffic condition and utilize these two knowledge to perform a real-time adjustment on my OD to come up with my best estimate of the OD that I should be using for my traffic simulation in real time. So that's actually the overall framework in a very conceptual manner regarding how you perform the real-time simulation of the entire city. To perform a real-time simulation, you need an OD matrix, and those OD matrices are actually adjusted in the real time by some of your observations, and then you are ready to perform the simulation. What I'm going to discuss is how you do the offline demand estimation. So if I have my traffic patterns with me, how do I get my OD matrices? And generally to do this, the offline demand estimation, what you know is your observations Y, X is what you have to estimate. And bi-level OD optimization is widely accepted and used in the literature. The way it works is you assume an OD matrix, you assign that OD matrix on your transport network, get an assignment matrix. Assignment matrix multiplied with the OD will give you the flows or the assigned flows on the network. And you try to minimize the gap between assigned flows and the observed flows. That's what you do. You keep on repeating it until the convergence is reached, or you are done with the number of iterations that you want to run. And once you get that, so whatever OD you get is the one that you use. There's a very well accepted, I would say, framework in the literature. But if you want to, like this framework is okay, theoretically it works fine, but there are a number of places where your new data sets or your big data can enhance the accuracy or the confidence that you might have in the OD estimation. First one is you might, with your, if I go back, restrict your search space at the upper level. Other one is you can apply the priori knowledge on the OD. You can come up with some empirical knowledge of the assignment, or you can also look at the ways by which you can perform the optimization. So your big data like trajectories and the speed can be utilized to restrict your search space, or you can basically look at different ways by which you can incorporate the priori knowledge. I might discuss about that. Let me first talk about, we have already seen the vehicle trajectories, how we can utilize these vehicle trajectories in the upper level. We have seen the Bluetooth-based trajectories that you can get those vehicle trajectories over the network. So currently, this is the bi-level framework where you use your loop trajectory counts to as an observed traffic volume, and you use it for your estimation of your OD matrices. That's the current framework. We worked on using the Bluetooth-based trajectories, and we use those trajectories as additional source of information to adjust our objective function at the upper level. And basically, the trajectories you get from Bluetooth, you incorporate that as additional knowledge in the optimization, so that you restrict your search space for which you are adjusting your OD matrices. So that's how you can utilize your Bluetooth trajectories to have more confidence in the OD estimation. That's one way of actually utilizing your big data to actually have more confidence in the demand estimation. Another way of also enhancing the accuracy is the lower level assignment is actually the most time consuming activity in this OD adjustment. You can utilize your observations from your trajectories and traffic states to come up with the empirical assignment for your lower level. For this, what we have done was, like, if I have my trajectories with me, those trajectories can give me a lot of information about how people are moving over the network. Between any OD pair, it can help me to identify what are the possible path choices that people take. It can also help me to calibrate my route choice models. and I can utilize that knowledge to actually come up with an empirical assignment. And that's what we have done actually in that project. Between one, like just as a proof of the concept, between one origin and one destination, we got all the possible trajectories. So what you see here are the routes taken by different travelers. We come up with an approach by which we can cluster these trajectories and identify the possible paths. So between this origin to that destination, I only have 5 paths, which were most likely used. And then I can also come up with the nested structure of the path and then utilize that knowledge to actually calibrate my route choice models. I'm not going into these details because these are already published works, but what I want to highlight here is with those trajectories that you get over the network plus other traffic state information, you can utilize them to have better understanding of your route choice behavior, and that can help you to come up with better assignment over the network. I would like to highlight the other ways, like in terms of how we can enhance the accuracy of the OD estimation. One of the ways we can do is by applying some prior knowledge on the OD, and this was the latest work that we have done, and we are still working on it. In fact, it's a PhD of one of my students, where what we are looking at is we are motivated by the video summarization techniques. Generally, you have like in case of video, you have a sequence of films in front of you, and in the video summarization, what they do is they take a sequence of films and then they perform some segmentation on those film sequences, and then say, okay, my entire video can be summarized in some of the key, I would say, frames, and that's a summary of my video. Now, we were motivated by this fact because our OD matrices are also a sequence of OD matrices. The dynamic OD matrices are a sequence of matrices. What we said that why do we have to adjust all the OD matrices? Why don't we just select some of the frames here? So come up with an approach by which we can identify the key frames in my sequence of OD matrices, and then once I identify the key frames, perform the interpolation between them, between the frames, and by doing so you can get the whole dynamic OD. That's the I would say motivation, or that's what we are doing right now. So instead of adjusting all the OD matrices for the day, we are looking at the ways by which we can identify the hook points or the key frames and perform the interpolation. It's an ongoing work, but we have implemented this within that Emerson Life framework. What I want to highlight here is, if you use, like, OD adjustment is very complex task. It takes a lot of time to adjust your ODs. For example, if you want to estimate an OD for 3 hours for the city of Logan, that one I showed you, it might take 8 to 10 hours to really come to a point where you have a small amount of confidence in the OD. If you use the Emerson approach of rolling horizon or simultaneous approach of 2 to 3 hours. With the keyframe interpolation, you can do the same job within 6 to 10 minutes. So the one which I've shown here with this framework, you can have a significant enhancement in the OD adjustment without much compromise in your accuracy. So what I wanted to highlight here is that these small, I would say, like these, the one which I've shown there, wait, 1 second, sorry. Those bi-level optimization framework, those these small changes that you can do in this overall framework can have a significant enhancement in your OD or in your demand calibration. And this big data set can really help you to achieve that. Now, so this is an ongoing research, and my team is working in this area. In fact, I have actually 3 PhD students working on different aspects of this. One of the PhD students is basically looking at the ways by which we can apply those video summarization technique to have better identification of the key frames and how we can perform the interpolation. The other research needs here is, we have not used the speed in the upper level of the tip function. So you can basically, we are highly underutilizing the amount of data that we have over the network. You can utilize that data set to further enhance your upper level of the tip function, and look at the moment you change your upper level of the tip function, you have to look at the ways by which you can optimize it, because if the function is not differentiable, then you cannot use the cannot use the gradient descent algorithm. So you might have to look at other ways by which you can perform the optimization. Plus, there's a lot of caliber that you might have with the detailed vehicle trajectory data set that can be utilized for the large network to maintain the quickly estimate or estimate the assignment or perform the better perform the route choice calibration. Plus, at this stage, we have only focused on the demand calibration, but you might like to also look at the joint calibration of both demand and supply using the multiple data sources. These are, other pieces of research that we have to do as part of these future activities. So the key message, which I would like to, again, I've already mentioned most of it. I've already mentioned this earlier, is that basically you have a lot of data set available to you. If it is available to you, then you can use it quite intelligently. Value and veracity are two important aspects. If you cannot extract the value out of your data set, then no matter how big data you have, it's useless. Veracity is very important. If you don't trust your data, no matter how big data you have, is useless. So have a proper understanding of your data set and look at the ways, because some data set can help you for some applications. They might not be applicable for other applications. So you should have an understanding of that. Said earlier, don't you use it blindly, especially machine learning and AI. They are just buzzwords. Have a proper understanding on the foundation before you move forward. That's all from my presentation. Questions? Happy to take more.
Thank you, sir, for a unique and enlightening speech. It has truly enriched us. Now the forum is open for discussion.
I might like to highlight actually one more thing. I mean there's no other question. I'd like to highlight that recently, sorry, this is not the slide we have. I don't have it here. We have recently, like other piece of things that we are doing here at KUT is we have recently launched Masters in Infrastructure. So, or Master in Sustainable Infrastructure, and we have actually been discussing a lot with industry regarding what are the needs or what are the skill sets which is needed. And one thing which was identified in the transport industry was the skill sets in terms of data analytics, visualization, modeling, simulation. There is a huge shortage of modelers in the industry. So, I mean, whatever I have presented actually are some of the in this area there is a very shortage of skill sets. We don't have a lot of modelers out there. We don't have a lot of programmers or data analysts with the transport background who can help us to really solve the problems which are there in the traffic modeling space. QT is offering a master in sustainable infrastructure, where we are developing new course in the area of smart transport and also in the area of smart hydraulics or smart sustainable water. So I want to just highlight that as part of my presentation. So if you have students who are interested to work in that area, or feel free to they can definitely contact me on that part.
Is there any practical instances to quote regarding the use of this application of this real-time data acquisition for the public transport optimization in Brisbane or in the locality?
Mm-hmm. So your question is for public transport. What are practical applications of this data set, how we can use it to actually better manage our public transport network? Is that your question?
Yes, sir. Specific to public transport services, depending upon the occupancy or the demand estimation, in the on a real-time basis, how to do the route rationalization or optimization for optimizing the public transport services.
I think that's actually is actually a very good question, and that I think is one of the areas that definitely, like especially in the Indian context, people should be working on. We know that a lot of interest is now towards electric buses, and many agencies and many cities are now adopting towards electric buses, and they're expecting that by next 10 years or by next 5 years or 15 years, depending on the agency, the buses will be electric. What we should be looking at is that most of the agencies have made their public transport data open in the form of GDF data set. I know Delhi has done it, perhaps Surat has also done that, and that data can be fetched from their server. Once you have this data set with you, you know how your existing public transport system is actually performing or behaving. What you can do is that's once you get those data set, you can start looking at ways by which, like in terms of optimizing your actually timetabling. So you know where my system is not performing well, or which of my routes are actually significantly delayed. And then look at the ways by which you might be optimizing your timetabling, taking into account the congestion effects on the road network. That is a purely optimization problem. Other thing that you can be looking at is for the electric buses, which I wanted to highlight, that electric buses will be rolled in a sequential manner. You might have some batches of electric buses coming first and so on. So identifying which routes to be electrified first based on certain characteristics, based on certain objectives, which might be in terms of the energy consumption or the greenhouse gas emission. Identifying like based on the battery capacity of the electric buses, how you should be rostering your public transport is another piece of optimization problem that actually has to be solved. So there are a number of, I would say, research that can be done on just utilizing the JDFH dataset itself, which is now widely available. I mean, you can even get that data for the entire city of Brisbane. I'm actually happy to share that with you. If you like we have already shared this here. You can download it from the using our codes, but I can also give the data because we are already anyway downloading it. I can just give you the data set for, let's say, 1 month or 2 months, just actually play with it. But you can use this code to even download the data for the city of Delhi, if I'm not wrong.
Sir, this is Anish. Actually, thank you for the presentation, sir. Even I'm actually working on this particular topic as far as the fusion of various data sources are concerned, so as to come up with OD on a regional scale. So, have you looked into the cellular data, because that is also widely available, might be in Australia also. So, have you looked at that data also?
Their cellular data set is a very it's very hard to get access to the data set. Like in Australia, we have different cellular providers, like Optus is one of them. And I had started discussing with Optus long time, about 10 years back, regarding can we have access to the data set. It was very hard. They never shared the data set, but they have utilized, well, they saw the potential in the data set to estimate the OD matrices. So they are selling the OD matrices from the cellular data set to agencies. So we have to look at what OD we are extracting from there, because those are based on the cell, like certain dimensions of the cell that actually they define. I don't have access to the data set, so I have not looked at the data set myself, but I do know that they do sell the OD matrices to the agencies by analyzing the cellular data that they have. But do you have access to the cellular data set in India?
We don't, sir, because it is restricted due to privacy concerns. So it can be accessed only by the legal teams. So we don't have actually, but might be we can have our hands on one of the data sets, but it's very rare.
It will be very hard. I mean, I can tell you, India, it was not possible at that time, 2011, when I was reading some, maybe I think Airtel has shared some data in some places, but I don't think it was ever shared. Cellular data set, I mean, it is because of they are storing the data set primarily for their billing purpose. For them, the initial use of the data is actually billing. But they did identify the potential of the data set for various transport modeling. So DSpark is one of the, I would say, companies spin-off from, I think it's one of the divisions of Optus, which is doing all this analytics using cellular data set. And then they are selling it as a service to the agencies. But as a researcher, having access to the raw data is almost impossible. However, whatever ODs they have sold to agencies is what you might be able to get. But I don't think you will be able to have access to their raw data set. So cellular OD will be hard to get.
Okay. Sir, could you please also share some light into how do we actually use the fusion of various data sets? Because as you said, there might be additive additions, or might be the same person is being tracked into different samples. So how do we actually come up with sort of a
Fusion.
Solution? Yeah, so that these double counts can be avoided.
So, I mean, if you do not know what's the source behind the data, it will be very hard to do that. For example, let's say I have a data from here. Here is one of the I would say service providers, which is I mean from a hair map. They also sell the speed profiles over the network, and you can basically use their APIs to extract the travel speed between any two locations that you specify. So here basic data set is, for certain hair links, they give you the average speed, they give you the number of vehicles used for that average speed, they give you how much confidence they have, and so on. So you can have one speed information from here. You can have another speed information, let's say from Bluetooth, and maybe the third speed information from the loops. So there are different sources which might be giving you different speed values for the same network. Then you might have to look at, okay, as an agency, I have now over information I have, and these speeds might not match. How do I fuse them together so that I have one single point of truth? So that's one of the challenges that agencies are facing, especially in Australia, that they have speed information from 3 different sources, and which one of them is correct, or what should be one single point of truth? So in that case, I mean, again, based on the confidence that you have in each of the data set, and that confidence can be expressed in terms of sample size or actually other characteristics. And then one simple way of doing it is just taking a weighted average where the weights are expressed in terms of the confidence. And that confidence can be further expressed in terms of sample size. So that's actually one kind of fusion. Other kind of fusion is actually, like the way we did for the loops and the Bluetooth. So loops are giving us counts at the location. Bluetooth is giving us travel time. So what we did was we had a cumulative plots that we defined from the counts. But these cumulative plots, we know they are going to drift based on the errors you have in the counting, and plus if you have the vehicles lost or gained in because of the middling source or sink. I mean, if you have, let's say, loops at upstream, loops at downstream, but there is some parking in between, your counts, your flows is never conserved. So what we did was you draw your cumulative plots, then based on your travel time profile, you basically readjust your cumulative plot so that you're not diverting a lot, or you're able to avoid the drift. By doing so, I mean, there's a paper that we publish on it. We call this as a Cuprite model. By doing so, you are able to actually utilize the cumulative plots to estimate the speed and the densities. So again, look at the data set, what the data is providing to you, and if you and look at your end applications, and then try to see how you can combine them together to get the best estimate. So I mean, these are 2 examples that actually you can. that might give you some idea about how to fuse them together.
Thank you, sir.
So this you're doing a PhD, or what are you doing?
Yes, I'm doing it on a part-time basis with IIT Palakkad and IIT Bombay.
Okay, and your PhD is on OD estimation?
It's on the, yes, sir, on the regional scale, transportation demand modeling on the regional scale for the whole Kerala state as well.
Okay. Mm-hmm. Feel free to contact
Tom
me.
and Prof. Okay.
Sure, sir. Sure, sir. Thank you, sir.
Sir, Samson, sir.
Yeah. Hello.
Yeah.
Sir, it's audible, sir.
Okay. So, Prof.
Sir, actually, Director NATPAC, Professor Samson, sir, he is on another program today. So he might be traveling. It's his network is not that stable, I think.
Yeah.
Sir,
I
Samson, sir.
can't hear it properly. Yeah, you're right.
I'm traveling. I'm traveling.
Mhm.
Support network connectivity also.
Mm-hmm.
Ask questions, they can do that. Well,
So probably he was telling the questions could be posted to you for further discussions on the topic.
No worries. Thank you. Yeah, sure.
So I think no more questions from the audience. So probably would like to listen from you more now. We will ask Arun Chandran to deliver the vote of thanks.
Hi, good afternoon. On behalf of NATPAC, I would like to extend my heartfelt gratitude to each one of you for joining us today for this insightful technical talk on the topic real-time simulation of large urban network leveraging big transport data. It has been an enlightening and thought-provoking session, shedding light on the advancement in the big data in transport engineering. Firstly, I would like to express my sincere thanks to our eminent speaker of the day, Professor Ashish Bhaskar, whose expertise and knowledge have truly motivated our audience. Thank you, sir. Thank you, Professor, for delivering an engaging and informative presentation. We are grateful for the knowledge and insight you have shared us with today. I would like to express my gratitude to all attendees for your presence and active involvement. The questions and discussion that followed the talk elicited your deep interest in the subject matter and are appreciated. I would like to extend my gratitude to our director, division heads and other organizing team for their meticulous planning and coordination that made the smooth execution of this program. In conclusion, I believe we all have gained valuable insights from today's technical talk, and let us carry this knowledge forward to achieve the goals. Okay, thank you everyone.
So once again, thank you, sir. Shalini here. We feel very blessed and honored to have you here with us today for this talk. Happy that I could meet you at WCTR and CTRG so that opened the way forward for this talk to happen.
Thank you. Thanks for. Yeah. Sorry.
We are thankful to our director also who had arranged this, who had helped us and supported us for arranging this. Thank you once again, sir.
Thank you. Thank you. The pleasure is all mine. Thank you very much, Sunny, for giving me this opportunity, and also an excellent audience who asked some good questions. My email is there. Feel free to send me email if you have any further questions, or if you need some further advice in your PhD or actually other career advice. I'm always available. So send me an email and I will try my best to come back to you.
Thank you, sir. Thank you so much.
Thank you.
So we'll stop this session, sir. For the
Okay.
day.
Thank you then. Bye-bye.
Thank you, sir. Bye. Have a nice day.
You too. Bye.
Thank you.